Hello and welcome to QED Stata 5 from part S11. We're going to do a hypothesis test to compare the level of internet access between men and women in rural Tajikistan. So it says write down appropriate hypotheses and use an independent t-test. So think about what the hypotheses would be, and remember, I will just write them here. Maybe I will just pause it so you don't have to watch me type. So I've typed in these H0 and H1. So H0, the mean response on internet access in the population, would be the same for men as for women. So I've copied that and put it in exactly as H1. So at the moment it's no good because it's exactly the same. But what has to be different is, what we're looking for is evidence to support a concern that men have greater access. So if we found in the sample that women had greater access, we wouldn't go for that. We wouldn't reject H0. So we're only looking here for greater, higher than for women. So I strongly recommend that you take the lazy way and make your alternative hypothesis by copying the null hypothesis and then just changing the bits that you need to change. So the null is the same for men and women, alternative is higher for men than for women. And then, right, independent t-test to address this question. So we need a bit of code for that to put into the do file. That's gone. Okay, let's keep that. So t-test internet, dividing it up by males and females. Let's see what happens. So it's done the t-test. So you've got 44 females, 49 males. That's the mean in the sample. So the difference in the means is quite small, but it's quite a big size sample. So the question is, if under the null hypothesis, where in the whole population the mean responses would be the same, what's the chance of selecting a random sample of 44 females, 49 men, and getting as big a difference as this? Well, as big a difference as this with the men ahead, which is the man is the second group here. So with this difference being bigger than 0 is 0.1059. So small, but it's not that small. So it's unlikely. So it's we can't reject the null hypothesis at 5% or even at 10%. So there's no strong evidence here that that men have got better internet access than women in the countryside. Though it's sort of slightly intriguing because it's a low probability, but it's not strong enough to reject the null hypothesis. So we don't have strong evidence here that men have got better internet access, as at least the mean responses are bigger. However, having said that, as it says, the two assumptions of the t-test are being violated really seriously. First of all, the internet access variables, it's ordinal rather than scale. So the meaning of these responses, if you look at the categories we're using, are not really, you can't really add these up. Like the difference between almost every day and less than once a week, sorry, not at all and less than once a week, that's not the same as the difference from here and here and here to here almost every day. It's much, much bigger. So doing some calculations, like doing calculations that involve mean and standard deviation and so on, means that you're sort of relying on the fact that it's scale data, which is that two people saying this is the same as one person saying this, and that doesn't really make any sense. So ordinal data, when it's like this, when it clearly makes no sense at all to add things up and calculate in that way, that's one big criticism. The other criticism is that for t-test, the underlying data should follow the normal distribution. And okay, if it's slightly away from normal, we can rely on the central limit theorem from that sampling theory that balances it out. But this is so incredibly skewed, you might worry that really, on top of the fact it's ordinal, using a t-test here maybe is a bit dubious. So as a cure to this, you can have a backup, which is there's a group of tests called non-parametric tests. This describes the man-Whitney U here. What that does is it takes all those numbers in the editor and it's put them together as they are here. And instead of taking the numbers, it just ranks them. So it takes the highest number, the next highest number, the next highest number, and ranks them from 1 up to 90 odd. as there would be. And then it says, what's the difference between the rankings, the average rankings that the male responses and the average rankings of the female responses? And runs a test on that and makes certain assumptions about the distribution. But the joy of these tests is you guys don't have to understand that fully to use it, though it helps you if you do. But to do it in Stata, you can say, okay, we're going to run that test. All you need to know is the command for it, which I'll give you. So you could say, okay, we're not sure it's normal, so we're going to try run this other test as well and see if that's compatible with this result. Actually, I want to write in the immediate window. I want to put it in the do file. Record it. So that's this. So rank sum. So it's very, very similar to the t-test, except it's based on the sums instead. There's the comment, tells you what it does. So just run that one. See if that's doing anything in Stata. It seems it doesn't. Yeah, it gives it a different, slightly different format. Looking at the sums of all the ranks. It's saying what's the sums of the ranks should be equal, of course, if there's no difference, but they're not equal, and the chance of them being that far apart comes out as, well, there's two ways it works it out. Either 0.147 using the approximate method, or 0.1795. It's better to use the exact probability if it's there. That's calculated theoretically and then calculated precisely. This uses an approximation because for larger samples, like if you had samples of thousands, this would take hours to calculate, so it gets impractical. But for our sample, it's quite small, it can calculate it quickly, so we use that one. They're both coming out, the important thing, as non-significant. Even though there's a two-sided, we've got to divide by 2. Even dividing those by 2, you're not going to get something less than 5%. But it is smaller. In both cases, it's less than 10%, so it's slightly more significant than the t-test answer is, but still not quite significant. So this Wilcoxian or Mann-Whitney test has given us slightly stronger evidence that there could be something going on here, but still it's that kind of level of weak evidence saying, okay, could be something going on, let's investigate further and gather data, rather than saying, hey, we're going to reject this at 95% confidence, because it's not strong enough for that. So conclusion is there might be some at least weak evidence that we need to investigate further to see if there's a difference, but the nature of the evidence, the highly skewed distribution, doesn't let us be confident about that. So bear in mind that these other tests you can use. The bad news is there's a billion different tests to learn. Great news is that the results, the way you interpret them, exactly the same in every case. Just look at that p-value and see, is it less than 0.1 or is it less than 1%, less than 5%. So the way you interpret it's the same, and it's very easy to carry out. Okay, so we've done that already. So we've done those 2 parts already, and now we're off to Madagascar, off the coast of South and East Africa. But for now, thanks for watching.